Hello guys, today I'll be explaining the chapter 9. I'll be doing a summary for chapter 9. So, let's start. First of all, in chapter 9, we started talking about chemical kinetics. Now, what exactly is chemical kinetics? Chemical kinetics is the study of reaction rates. Basically, anytime you see reaction rates, that means we are talking about chemical kinetics. Since our chapter is about chemical kinetics, it will, just from the name, we can know that we're going to be studying about the reaction rates and what affects them and how it slows down, how we measure it, and basically all of this in chapter 9 we'll be talking about it. This is in the chemical kinetics, which is the study of reaction rates. Now, we have a reaction. We're going to denote it from now on as Rx. So the reaction rate, Rx meaning reaction, the reaction rate is measured or calculated. So of course, if we have a reaction, we need to measure or calculate its rate. We can either measure or calculate its rate by the quantity of products produced per unit time, okay? Meaning, you can measure or calculate the reaction rate by the quantity of products being produced per a specific unit of time and the quantity of reactants consumed per unit time. Or we can say that it is the quantity of reactants that are being used, being consumed in the reaction per unit time. Let's take an example. Let's take 2H2 plus O2 gives us 2H2O. All right? We can, to measure or calculate this reaction rate, we can do it by the quantity of H2 consumed. Why? Because H2 is our reactant. Or the quantity of O2 consumed, because O2 is our reactant. And don't forget per unit time, very important, per unit time. Or the quantity of H2O produced, because it is our products. Now, if we had the inverse, which is 2H2O, gives us 2H2 plus O2, how will we measure or calculate it? We can measure it by the quantity of H2O consumed or the quantity of 2H2 produced or the quantity of O2 produced. So if it's in the reactants, we need to measure it by the quantity consumed. If it's in the products, we need to measure it by the quantity produced. Now, of course, we have something different than measuring or calculating reaction rates. We have something called studying. So studying reaction rates. I'm gonna label reaction as Rx, okay? So to study the rate of a given reaction, we have two ways to do it. Of course, it depends. So sorry, I had to cut off. So to study the rate of a given reaction, it of course depends on the reaction. If for example the reactants are gas, liquid, solid, or if it is an inverse reaction, if you reverse the reaction, it of course depends on the reaction. Whatever it is, it will depend on it. Now, how do we study the reaction rates? We have two ways to do it, which is the volume of gas produced with time. So, to study the reaction rate, one way of doing it is to measure the volume of gas produced with time. So if we had, for example, 2H2 gas plus O2 gas gives us 2H2O gas. To study the reaction rate of this reaction, okay, we have to make sure that, first of all, our products are gaseous. Why? Because we can only measure the volume for gases. So we have 2H2 gas plus O2 gas will give us what? 2H2O gas. Our product is gaseous, so then we can measure its volume. So to study this reaction, we can measure the volume of gas produced with time. Another way of studying is the change in mass with time. So don't mistaken this for doing the mass of the products minus the mass of the reactants. You will get zero, because the law of conservation of mass, okay, says that whatever mass we have in the products will stay the same as the mass in the reactants. But instead, they're saying while the reaction is happening, okay, check how much mass in the reactants is decreasing per time, or how much mass in products is increasing. So let us say we have reactants give us products. Throughout the time, we're gonna have the reactant initial, the mass is gonna be, let's say, 4 grams. Then, over time, the reactant final, the mass is gonna be 0 grams. Let's say this is over the span of 5 minutes. Now, the product initial, the mass is 0 grams. Whereas the product final, the mass will be 4 grams. And this is over the span of what? 5 minutes. So, if they ask you to find the change in mass with time, we do not do the change of mass of products. Sorry, we don't do the mass of products minus the mass of reactants. No, we do the final mass of reactants minus the initial mass of reactants, or the final mass of products minus the initial mass of products. So here you're gonna get negative 4 grams, and here you are gonna get 4 grams. Now, of course, you have to say this is for the reactants, and this is for the products. So this is how to study the rate of a given reaction. Now, we're gonna draw a graph. I might cut the video and then I will draw the graph. Okay, so this is our graph. This is our graph of what? Of reaction rate. Meaning that the slope is our reaction rate. Okay? On our x-axis we have the time, and on our y-axis we have the products. I will say just in advance, I know it's been 10 minutes into the video, but chapter 9 is all memorization, okay? More logical if you want me to put it in this way, but there's not a single equation in chapter 9, so you have to memorize most of the stuff, okay? So this is our reaction rate slope, okay? The x-axis is time and the y-axis is the products produced. If you notice over here, a lot of products are produced in a small amount of time. So we say that this reaction over here is fast. As it comes closer to the curve, okay, the amount of products produced per a certain amount of time decreases, so it starts slowing down. okay? Then finally at the end it becomes a constant straight line. It becomes the plateau. So here, reaction finished. Now, we can then make a general rule that in the reaction rate graph, at the beginning it's faster, then towards the curve it starts to slow down, and then at the end, when no more products are being produced, the reaction rate has finished. Now, we're gonna be discussing something called the collision theory. So I'll write the definition of collision theory, then we will go into deep meaning. So it is the particles of reactants must collide with one another with a minimum energy called the activation or threshold energy. I wrote threshold wrong, just 1 second. There's only one H. So the threshold energy. Now this is writing. Let us go into explanation. The collision theory, particles of reactants must collide with one another with a minimum energy called the activation or threshold energy. So, for a successful reaction, what does the collision theory state for a successful reaction? The particles of the reactants. So again, for a successful reaction to happen, the particles of the reactants, that means they should react. If they are gonna react, they must collide, they must hit each other with a minimum energy called the activation or threshold energy. In other words, in a brief summary, for a successful reaction, particles must collide with energy So particles must collide with energy that is greater than or equal to the threshold or the activation energy. Again, the collision theory states that particles of a reaction, mainly the reactants, for them to do a proper reaction, they must collide with one another with a minimum energy called activation or threshold energy. In other words, for a successful reaction, particles must collide with energy which is greater than or equal to threshold or activation energy. Now, we were talking a lot about the reaction rate. Now we'll be talking about how we increase the rate of a reaction. So, to increase reaction rate. Logically speaking, we said for a proper reaction rate to happen, they must collide. So if we increase the number of effective collisions, so increase number of effective collisions, then we would have increased the reaction rate. But this is the thing, how do we increase the number of effective collisions? We have multiple ways, and we will go to each and every single one of them into detail and to which type it affects. Okay? So the first thing we have is surface area. The surface area, we have either a big block, okay? This is a small surface area, or we can transform it into smaller blocks. Okay, then this has a big surface area. Now, why is it important, surface area? If we have a bigger block, it would take more time for the reaction to occur, so the reaction is slower. Whereas if we had a smaller surface area, like the small blocks, the reaction would happen in a quicker time, so here the reaction is faster. So then we can make it as a rule: if we increase surface area, then the reaction rate would increase. Now, the surface area only affects solids and some homogeneous mixtures. Alright? So, quick summary about surface area. If we have a small surface area, then the reaction will be slower. If we have a big surface area, then the reaction will be faster. So then we can say that if we increase the surface area, then the reaction rate increases. Okay? And then the surface area affects only the solids and some homogeneous mixtures, nothing else. Next thing we have is the temperature. Temperature. When we increase the temperature, the speed of the particles will increase. So if they are moving faster, then definitely if they are in the same container, they are more likely to hit each other. So if they are more likely to hit each other, that means we increase the reaction rate. So as we increase the temperature, then the kinetic energy or the speed will increase, then the reaction rate will increase. Okay, now the temperature affects basically all, so solids, not all, but like it will affect, like it won't really affect solids that much, but still it will make their particles move faster and they will collide more. Okay, then it affects liquids very much. It affects aqueous solution very much. Now, what's the difference between liquids and aqueous? Liquids can be any liquid. Aqueous, liquids as in solutions, I mean here. Aqueous is a solution. Now, aqueous solutions is different from liquid solutions. In which sense? In the sense that here the main solvent is water. Okay, so remember, liquids, aqueous, and gases, they are all affected by the temperature. And solids are affected just a little bit by the temperature. Now, after temperature, we have concentration. Concentration is the most important one. Now, what is the concentration? What does it affect? It can affect solutions, mainly aqueous solutions. So we're going to say here aqueous, okay, and gases. What does concentration mean? It means the number of particles. So if we are adding more particles into the aqueous solution or into the gases, then definitely the reaction rate will increase. So a higher concentration, this is how we denote concentration, okay, a higher reaction rate. Now, after concentration, we have volume and pressure. I'll put them in one because they affect each other, the volume and pressure. We have a small box and a bigger box. If we have 1, 2 particles here and 1, 2 particles here, where are these 2 particles of the same size, of the same mass, okay, in both boxes, where are they more likely to collide? Definitely in this one. So the smaller the volume, the greater the reaction rate. Now, pressure is inversely proportional to volume. So we can say P is inversely proportional to volume, meaning that as we decrease the volume, the pressure will increase. So that means a decrease in volume will increase the reaction rate, and an increase in pressure will increase reaction rate. Now, when we're talking about volume and pressure, we only talk about gases. The only thing affected, the only state affected by volume and pressure is gases. Now, last but not least, we have catalysts. Catalyst, I will write something really quick, then we will go later in the explanation into a deep meaning about catalyst. So, if you increase the amount of catalyst, then you will increase the reaction rate. So definitely, an increase in the amount of catalyst will increase the reaction rate. We will see later on why. Now, after explaining about the things that affect the reaction rate, okay, we are gonna draw a graph and we're gonna explain the graph. Now I will cut the video and I will draw the graph and come back. Okay, so this is the graph. We're gonna take the red as our reference level. Okay, reference level, it means it is the basic without any changes. Okay, the basic reaction. All right, now we're gonna discuss what each one does. So I'm gonna write them all here. We have surface area, then we have temperature, then we have concentration, then we have volume and pressure, and then we have catalyst. Now, in advance, we're gonna say that the surface area, the temperature, the volume, and the pressure, and the catalyst only affect the slope. So I will write it here. They only affect the slope. Whereas the concentration, and more specifically, concentration of limiting reactant or acid, will affect both slope and plateau. All right? So since we know that the surface area, temperature, volume, and pressure, catalysts as well, they only affect the slope, and the concentration of limiting reagent or acid will affect both the slope and the plateau, we can proceed to decipher which one is which. So let us say, for example, we increase the surface area, okay? An increase in the surface area will increase the slope, and only the slope. So if we go back here, which one only affected the slope? The blue. So here we say increase in surface area. The temperature, if we increase the temperature, then the reaction rate will increase, but it will only increase the slope. It will only affect the slope. So which one affected only the slope? It's the blue one, so it's also an increase in temperature. If we decrease the volume and increase the pressure, it will cause an increase in the reaction rate, which then causes an increase in the slope. And we said if it's only affecting the slope, then it's the blue one. That means lower volume, higher pressure is affecting the blue one. Okay? Now finally, the catalyst. We said if we increase the amount of catalyst, then definitely only the slope will be increased. So the blue one is the catalyst. So notice that the surface area, temperature, a decrease in volume, an increase in pressure, and the increase in the amount of catalyst will only increase the slope. Now, the concentration of limiting reactant, let's say we have excess is R1. I'm just giving examples. And excess, not excess, sorry, my bad. We have already our excess, which is R1, and we have the limiting are 2. Okay? So, if the concentration of the excess increased, it will not affect anything. Why? Because we have a limiting reagent. The limiting reagent is like once the limiting reagent finishes, the excess we will have remaining of it. So if we increase its concentration, it will have no effect, but we're gonna have more excess remaining. However, if we increase the concentration of the limiting, okay, then we are increasing the amount that can be produced. So definitely the slope, not only the slope, but also the plateau will be affected. So again, if we increase the concentration of excess, it will not do anything but give us more excess. Okay. However, if we increase the concentration of the limiting, then we will increase the amount of products being produced. So definitely the slope and the plateau will increase. Same goes if you decrease. If you decrease the amount of excess, the concentration of excess, it won't do anything. But if you decrease the concentration of limiting, it will decrease the amount of products being produced. So it will decrease the slope and the plateau. So that is it for the reaction, what affects the reaction rates. Now, just a small note that if you increase surface area too much, then explosions may occur. All right? So if we increase the surface area too much, then explosions may occur. So definitely, we have to pay attention to how much we increase the surface area. Now, we also remember that the surface area will only affect the solids and some homogeneous mixtures, but it only affects solids, mainly. Now, we will be discussing something called activation energy. We talked about it from before. It's also known as threshold energy, and it's the minimum energy that reactants should collide with. So, as a note, activation equal threshold, okay, equals minimum energy for collision. Now, we will be drawing some graphs, and from this graph, we will be explaining. All right, so give me I'll pause the video, then I will continue it. Okay, so we have our first graph, which is the exothermic graph. We're gonna start. In the exothermic, we know that the heat of reactants is higher than the heat of products. Okay? This red arrow over here represents the heat of reactants, or the energy of reactants. And this arrow over here represents the heat of products, or the energy of products. Now, at the very, very tip of this curve, okay, this is called the activated complex. Logically, if this is the activated complex, then this arrow from the reactants to the activated complex, okay, this over here, we will call it the activation energy. Now, of course, we have the forward activation energy and the backward activation energy. In the CQDs, we will experience them, and I will explain them, so don't worry. And so we know from before that the heat from reactants to products is what is delta H, or our enthalpy change. So this is our exothermic graph of activation energy. We also, of course, have endothermic. We know that in endothermic, the heat of reactants is lower than the heat of products. All right? And this energy over here is called heat of reactants, and this energy over here is called heat of products. Okay? And this energy from the reactants to the very tip of the curve, we call it activation energy. And the very, very tip of the curve, we call it the activated complex. All right? Now, this arrow going from the reactants to the products, we said always from the reactants to the products, it is delta H, which is our enthalpy change. So that is it for the activation energy. Now we'll be talking about catalysts. I'll be writing some bullet points about catalysts. Just some general ideas. A catalyst is a substance that increases the reaction rate without being consumed. So how does it increase the reaction rate? When increasing the reaction rate, it speeds up forward and backward reactions. Okay? Now, it does not affect delta H, all right? And it gives us a lower activation energy or a new pathway. And then finally, it is regenerated at the end. Now, just some small general ideas. We don't need a big amount of catalyst because they're very effective. They're very specific. So for every substrate, if you learned it in biology last year, for every substrate there is a specific catalyst, and it's very sensitive to temperature and acidity, so it will get denatured if the temperature is too high or if the acidity is too acidic. Okay, so these are catalysts. If you increase, they will increase the reaction rate without being consumed. They speed up forward and backward reactions, and they do not affect delta H. They lower the activation energy in new pathway, and they are regenerated. So let's take, for example, this endothermic. Okay, wait. Let's take, for example, this endothermic graph. I will copy it, and then I will come over here, and then I will paste it. So we have this endothermic graph. We have in black, okay, in black we have the activation curve but without a catalyst. So we said that what does the catalyst do? It speeds up the forward and backward reactions. So this is the forward reaction, and then you will get the backward reaction, which is like this, okay? So it will speed them up. If it speeds them up, then they will become shorter. So let us say that now we need a new color. Let's say this pink, okay? This pink is now our new forward and our new backward reaction, okay? So let us then draw the curve with respect to the new forward and backward reaction. There we go. So what can we say now? We can say that because of the catalyst, due to the catalyst, the curve or the activation curve is lower, okay? So it is a new pathway. Let us also do the exothermic, because we did endothermic. Let's do exothermic. So Control C, paste it here. Okay, here we have our exothermic. Let's say we added a catalyst, okay? if we add a catalyst, we said that the forward and backward reactions would decrease. Here it's very small, so I'll make it tiny. So now, if in the red it was our old forward and backward, and now our pink became the new forward and backward, okay? Then, if we're gonna redraw the curve, but with respect to the new forward and backward, it'll be like this. Notice how the curve is lower. That means the activation energy is lower, okay? That means it will happen faster. So, thank you guys for watching. I hope you enjoyed and have a wonderful day.